Good morning, humans. So first off, I should apologize for yesterday. There was some confusion on my end about question 3 from the exam for some of the versions. Um, I basically just screwed up, and I'd like to sincerely apologize. Um, yeah, this happens. Life is not always perfect. But I'd like to apologize if I caused any additional stress to people, and or I made life not as fun for some. So I want to say sorry. Hopefully this doesn't happen again. But we all make mistakes. We're all human. And I hope that you all are okay with that. Speaking of mistakes, a second mistake that I talked about was that this note in my notes was incorrect, in particular here. The derivative is not this. There should not be a square root here. So the derivative here is actually minus 1 over 1 plus x squared. It's correct in other parts of the notes, but it's not correct here. So I figured I'd let you know in case you need to use this. So yeah. All right, so let's go over kind of what we were going over on Monday. And let's talk about how to calculate areas under curves. And so remember what we were kind of doing is we started trying to find some way to rewrite these long summations as into something a little more concise, right? So we were having problems of 1 plus 1 plus 1 all the way up to plus 1, 25 times, right? This versus like 1 plus 2 plus 3 plus 4, blah, 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 to plus 25. And so we were starting to wonder, how do we show this in a nice, concise manner? And we started using what's called sigma notation. So we added this symbol sigma here in order to denote a summation. So sigma for summation, S and S. And basically what we decided to denote it as is this thing here. So we have this summation, and this is a general way to write these summations. So what we have, if you recall, is these AIs are little functions, where we have a and then we sum over from I going to m to n. So what we do is we change these little indices here, going from m all the way to n, always adding 1. So we have m plus 1, m plus 2, blah, 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 all the way to n. And to see this, you can kind of see these in the formulas above, in the summations above. So here, my AI was just 1 on the left-hand side. And the example on the right for the sum of I, this is just, our AI is just equal to I. So I just plug in each I one at a time. So I get 1, 2, 3, all the way up to 10. We can make this also go all the way up to infinity, and we do this sometimes. But for now, let's look at some finite examples. So here's one example. So if I take my summation, right? So here I have my normal summation, sum of I equals m to n of AI. We're going to pretend this is our summation. So m, I'm going to set equal to 1. N, I'm going to set equal to 4. And my AI is this. So AI is 2i minus 1. So what do I do? So here's my 2i. So here's my I equals 1 case. Here's my I equals 2, right? So I have 2i minus 1, 2i minus 2. Here I have I equals 3. Here I have I equals 4. So remember, we're going from 1 to 4. And so this is why we have 1 through 4, etc. So here we can plug these numbers in. So we get 2 times 1 is 2, minus 1 is 2. Oh, wait. I did this backwards. So I have 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, and then I have 4 minus 1, so I have minus 4, and then if you add these together, you end up getting 16. So let's look at the next example. We're going to look at, this is a little hard to read, sum from I equal to m of n, bi. So I can change these variables, right? AI doesn't actually mean anything, so I can have bi. And that's perfectly okay. So we're going to go from I equal to 3 to 5 of I squared plus 1. So we start off with 3. So we do 3 squared plus 1 plus the next one is 4. So 4 squared plus 1. Next one is 5. So 5 squared plus 1. So here we get 9 plus 1 plus 16 plus 1 plus 25 plus 1. And if you add these up in a calculator, you get 53. And then these variables, remember, they're just variables. We can change the letters up and it won't matter. So here's one that's a little crazy because we got to craze things up a little. So let's look at the sum from j is equal to x to y of I sub j. So in this case, j is my index. So j is what I'm going to be updating. X is going to be my lower. Y is going to be the upper limit. So what do we have? I'm taking j from -4 to -1 of 3. So this means I have, so I of -4, this is 3, plus I of -3, right? We add 1, is 3, plus I of -2, this is 3, and then I of -1, this is 3. So here we have j is equal to -4, j is equal to -3, it's all the way to j is equal to -1. And so here the -4 is our x, and then the -1 is our y. So here we have 3 plus 3 plus 3 plus 3 plus 3. This should be easy. This is just 12, yeah? And we can actually do this backwards, right? So if I have some summation, I can write this in summation notation. Fun little rhyme there. Summation notation, bring it. And so what do we have here, right? So if I have 2 5 times, I can just start it from I is equal to 1. I have 5 of them, so I'll do it 1 through 5. And then I'm adding 2 each time, right? So this is going to be my I equals 1, I equals 2, I equals 3, etc. So let's try this with another one. This one's a little more complicated. But let's state that this is going to be I equals 1, I equals 2, I equals 3, I equals 4. So I have 4 things. So what I'll start right away is just say I equals 1 to 4. And so let's try to calculate. So this is the hard part for these, is to try to calculate what this function is going to be. All I know is it's some function of I. And the thing I'm going to notice here is that, and these don't care too much. It doesn't really matter. This is just more things you should have kind of learned. Here, notice how I'm adding 3 each time. So the idea here is that it's probably 3 times I plus something. So I have 3 times I, right? Because each time I'm adding, for each I add 1, I'm adding 3. So that's where this 3i is coming from. And then in the first case, I equals 1, I have 5. So really I should have 3 times 1 plus 2 should be 5. So this should be 3i plus 2. And if you check, you get the same thing. But these indices we can actually change, right? I can actually pretend that this is I equals 2 in the beginning, I equals 3, I equals 4, I equals 5 if I really wanted. And then this would actually change how I calculate things. And I would get this summation. So these summations are not necessarily unique. There's multiple ways I can write the same summation. So let's look at this one. I have this, and it looks like I'm just adding the numbers from 1 to -3. So this looks like something we've done before, right? Just adding numbers. We just did I. But here I'm taking my I from 1 to -3. Since the 1's the bigger one, I'm going to put the 1 on top, and I put the -3 on the bottom. This doesn't matter, right? Because these I can commute. This is the same thing as -3, -2, -1, plus 0, plus 1. And so this will give us a summation for this. And like I said, don't worry too much about this. These are a little difficult, but there's a lot of properties that kind of help us. And so these you've probably seen not a million times. You've probably seen a few of these before. And basically, we've kind of seen these, right? So here, the first one, we can change notation. This is saying notation doesn't matter. The second one basically allows us to change indices. Notice how I'm taking it from I equals to m to n to I equals 1 to n minus m plus 1. This is what we did in the second one of the last example. So change indices. This third one allows us to break it up. So basically, if I want to go from m to n, I can look at everything from 1 to n, and then I can remove everything from 1 to m minus 1, right? Number 4 is basically saying the constant. If I do a constant, I'm just going to be multiplying this constant n minus m plus 1 times. And this comes from, if you think about it, n minus m minus 1, right? Because this is the n here, and then this is the m minus 1. So this is where this is coming from. Similarly, if I have a constant times some function, I can just bring out the constant, right? And this is coming from if I have CA1 plus CA2 plus CA3, etc. I have a C in all of these, so I can just bring out the CA1 plus A2, etc. And I don't really change anything, and that's okay. So let's look at 6. If I have two summations, I can split them apart. That's okay. Telescoping sum, this is fun. If you've never done a telescoping sum, they're super fun to work with. And basically, this should actually end up being a n minus a0. Try it out. Test this out. Fun. Do it at home. I used to have so much fun with these, mainly because I'm a bored child. But if you're not doing anything, this could be something nice to do. Some other things, let's see. If I have n from I is equal to 1 to n, I have I. This gives me n times n plus 1 divided by 2. And then we can do similar things for I squared, I cubed, r to the I, etc. Notice that these indices do matter, right? If we change the indices, we're going to have to look at property 2. We can't just change indices without changing our function itself, yeah? So just note that. So we can actually use this information to help us with our problems. So for example, if I have this summation, sum of I equals 1 to 100 of I, well, this I've seen this, right? This is just number 8. So this is 8, right? So this is n times n plus 1 over 2. So here my n is 100. So here's n. This is n plus 1 divided by 2. So I get 100 times 101 divided by 2. And so I get that. Fairly easy. Here is something a little more complicated. Let's look at k from 5 to 12 of k squared. So I have 9. I can use 9 if I want, but I really can't, right? Because the problem with 9 is that these indices have to start from 1. So I can't really use 9 here. So I'm going to remove 9 because I can't use it. But there is a way to lower these indices down to 1, right? And this came from number 3. So I can split this up into k is equal to 1 to 12, k squared, minus all the way to 4, right? So I take out everything from 1 to 4. And here, these are both 9s, right? Here I can use 9, and that's okay. And so what do? I plug it in. So I have, the first one I have 12 is my n, times 12 plus 1, times 2 times 12 plus 1, all divided by 6. But I have to now take away this 4 case, right? So 4 ends up being 4 times 4 plus 1, 4 times, or 2 times 4, sorry, plus 1, divided by 6. Now, if you plug this in, this should give you, what do I get? 2 times 13. So here I cancel these and I got 2. This gives me 13 times 25. And then here I have 4 times 5 times 9 over 6. So we have 650 minus 30, which is just 620. So this big summation, right? So this, if you think about it, right, is 5 squared plus 6 squared plus 7 squared plus 8 squared plus 9 squared plus 10 squared plus 11 squared plus 12 squared. This whole thing, oops, we just calculated in just a couple steps to get 620, right? This would take a lot longer. Imagine doing this over a much bigger case, right? So here, let's stop for a second, take a pause the video, and try this problem out. I'm using the formula from above. So use these. And for each step, like I did here, make sure to state which rule you're using. Yeah, you need to state which rule you're using for these problems. So hopefully you paused and you tried it out. What you should end up getting is the following. You should get 2,460. If you didn't get that number, ask a friend, talk to me, etc. You should have that number.